All right, so for today, we're going to continue our study of more derivatives. In particular, we're going to take a slight detour and focus on one particular type of function. So as you can probably see from the title already, we're going to go ahead and talk about the derivative of trig functions. So as a reminder, someone go ahead and give me just examples of random trig functions. What's probably one trig function you're thinking of? Like sine of x, cosine of x, tangent, all of those special things that you may have learned and may have forgotten from geometry way back, or if you took trigonometry as well. So a lot of these trigonometric functions come from, well, trigonometry and how we studied triangles and the angles on those triangles. And then we were able to extend that to pretty much any angle if we wanted to. But that's not going to be our main focus. We're going to be focusing on the derivative of the functions themselves. So for these first couple of slides, you don't have to write down what I'm writing for these first couple because this is just going to be the theory behind it so that we know where does it actually come from whenever we actually introduce the theorem. So for like the next 3 slides or so, I want you to more or less just pay attention and listen rather than trying to write down everything I'm saying here. All right, so to build up the derivative of the trig function, the theorem, again, we're going to try to figure out what's the derivative of sine, what's the derivative of cosine, what's the derivative of tangent, and all of that. In order to prove that, I will need some preliminary information. So I'm going to start off by introducing these 2 special limits that are going to be helpful for me. The limit as x goes to 0 of sine of x over x is equal to 1. And then the limit as x goes to 0 of cosine of x minus 1 over x is equal to 0. And I'm actually going to go ahead and write those on the board so that I have them for reference later on. Again, this is not something that we're actually going to be working with. This is going to be for the background on how we get there. So right here on the side, I'm going to just need it for reference for myself. We have the limit as x goes to 0 of sine of x over x is equal to 1. And then the limit as x goes to 0 of cosine of x minus 1 over x is equal to 0. Again, keeping those for reference on the side. Furthermore, I'm going to introduce another concept from trigonometry. And just so that I have a little bit of a background on y'all, how many of y'all have taken trigonometry before? More or less, I'm not saying if you can recite it back to you, but you've taken it more or less. All right, good, because that's generally one of the prereqs for this course, that you know a little bit of trig. If not, don't worry, we're still going to work with it and everything like that. So this is one theorem. The reason I wanted to do that is I wanted to reintroduce this old theorem or identity from trigonometry called the sum and difference identities for sine and cosine, which tells me, first off, if I want a sine of a plus b, 2 numbers or 2 angles, this is equal to sine of a cosine of b plus cosine of a sine of b. And the same thing for cosine. We have something very similar. So just like before, I'm going to just write this down on the board for reference so that I have it for later. Sine of a plus b is equal to sine of a cosine of b plus cosine of a sine of b. Yeah, sine of b. And then cosine of a plus b is equal to cosine of a cosine of b minus sine of a sine of b. Again, just keeping these on the board for reference. What was that? You could use this for a physics class, maybe not as intensely as what we have here, because generally for physics, you're probably just going to say, you might put into your calculator sine of 30 or sine of 50, something like that. Whereas whenever we're talking about this in respect to a math class, we care a little bit more about the actual value, because it's going to be some weird decimal, stuff like that. So it can be used for physics. in certain applications. All right, so I'm going to go ahead and consider this. What's probably the first trig function you probably ever learned or have seen? Starts with an S. Sine. So sine is usually the first one that people get introduced to. So that's what we're going to start off with today. So if I have, I don't know, let's call it f of x is equal to sine of x. Let's say that I want the derivative f prime. Again, this is just the background. This is not something I would usually ask for you to prove yourself. So if I want the derivative, I'm going to go ahead and use the limit definition of the derivative that we learned a while back, which we remember now that we've finished the exam. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. Or in this case, if I just plug in as needed, f of x plus h. That would be sine, and then in parentheses, x plus h. Sine of x plus h. Minus my original function all over h. So this is me trying to figure out what is the derivative using our old way of using the limit definition of the derivative. All right, so looking at this, there's no obvious way that we can simplify this, which is why I put this on the board. I know how to break down sine of x plus h. That's exactly this identity right here. So it's going to look a lot worse before it gets better. Sine of x plus h. Instead of a and b, I got x and h. This becomes sine of x cosine of h plus cosine of x sine of h minus sine of x. I'm being a little bit lazy, not putting the parentheses, all over h. All right, so we're going to go ahead and try to clean this up. So sine of x plus h, I just applied my sum identity for sine. What was that? They're not going to exactly cancel out because it's not just a plain sine of x minus a plain sine of x. But here's what I will do. This is equal to the limit. So really, I'm just pushing and seeing how far we can take our trig and algebra skills here. First off, would you all agree that both of these have a sign in them, a sign of x? So really, if I look at this expression and this expression, I should be able to write this. Sine of x times cosine of h minus 1. So this part is the same thing as what I circled. I can take out a sine of x if I wanted to. Plus cosine of h all over h. So again, I took these two things I circled. They both have a sine of x. So I can factor out a sine of x from them. So if I take sine of x out from here, I'm left with cosine of h. If I take a sine of x out from here, I'm left with a negative 1. And then I still have, oops, I forgot, I accidentally, let me add this here. It's not just a plain cosine. That should be cosine of x, sine of h. Like so. I went a little bit ahead of myself. And this is just being brought down from before. All right, so I'm going to keep on cleaning this up and let's see where it takes us. I've used this side of the board already. I know eventually I want to use this somehow. So let me go ahead and I ran out of room here. Let me erase this top half. Yeah, go ahead. Unfortunately for this one, I can't just shift it up like the other board. All right, so I'm going to erase this top half right here. Lines 1 and 2. I'll call it that. All right. One thing I know about limits is that limit of a sum is the sum of the limits. In other words, I can break this down into the limits as h goes to 0 of sine of x cosine of h minus 1 all over h plus another limit of my other stuff, cosine of x, sine of h all over h. So this is using one of our old rules for limits. You can just take the limit of each part of your sum individually. Now we're almost there. Looking at this first one, I'm gonna write this down first and then explain what I did. So it looks like I took a sine of x out to the front of the limit. So the first question I want to ask is, why am I allowed to do that? What is this limit? What are we plugging in for usually? H's. Does this sine of x have anything to do with an h? Because that sine of x has nothing to do with an h, we're allowed to move it around to the front. It's kind of like if there was a 3 on the inside, we can take the 3 out. Because the sine of x has nothing to do with h at all, I'm allowed to take it out. And I'm going to do the same thing over here. This cosine of x got nothing to do with my h limit. Sine of h all over h. Erasing this bottom line now. All right, so I have sine of x. What is this limit equal to? 0. Is that here instead of x's, I have h's here. So this whole thing is 0, which is why I gave it to y'all earlier. We could prove that, but just for the sake of time, I'll say it's 0. Yeah, what's the other limit? 1, because this is sine of h over h. All right, what does this all clean up to after I multiply it out? Yeah, so right here, I think we agree that's 0, right? Because that's 0 times sine of x. So that's 0 plus cosine of x times 1, that's just cosine of x. So we get cosine of x. So using some trigonometry and some algebra skills, we can actually see that the derivative of sine does turn out to be cosine. So a lot of work to go make this larger and then go back to another trig function. So we know that the derivative of sine is equal to cosine, and we've just shown it using the old limit definition. We started with f of x is sine, and then we eventually ended up that f prime, the derivative is cosine. So obviously I'm not going to be asking you to use this limit definition because first off, this is very long. And how many trig functions do we usually work with? Let's see, we have sine, we have cosine, we've got tangent. There's 6. 6 trig functions means that there's 6 derivatives. So let's go ahead and X this out. I didn't want this to show up early, but we know the derivative of sine is cosine. I was expecting this to show up later. It turns out the derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent. And then derivative of cosecant is equal to negative cosecant cotangent. There is a pattern. So first off, this is now where we will start copying down our notes. 6 trig derivatives, 6 trig functions means that there are 6 trig derivatives. And to answer any preemptive questions, yes, you will need to know all 6 trig derivatives. One thing I want y'all to do while y'all are copying, why did I present the 6 derivatives in this particular order? See if you can see a pattern between how I arranged it on the board. Probably first write it and then try to see if you can find a pattern. Again, there's a very particular reason why I put it in this order instead of just putting sine, cosine, tangent, and then the other 3. So again, I'll give you some moments, and then while you're doing it, think about the pattern that we see here. I will know that all of these are stuff that we could have proven, like what I did for sine, but again, at that point, it's kind of tedious that we're doing the same thing over and over again. So what's going to happen for probably the next 2 weeks, give or take on and off days, I'm going to start off with just saying, all right, give me the derivative of sine, or the derivative of one of these random trig functions. One small note I want to make also just in general about trig functions. Here I said derivative of cosine is negative sine, but if I want to be exact, I should be saying the derivative of cosine of x is negative sine of x. So whenever we think of trig functions, for example, this is not something that you have to write, just a side note. You're never just going to write this. It has to be sine of something. Sine of 4, sine of x, sine of theta. It has to be sine of something. In this case, I wrote a theta. The reason that I wanted to mention this is that every semester, sometimes a student will get to this point. And then what they try to do to solve for x is they write this. That's not something we can do. If I just write sin by itself, that means nothing. It has to be sine of something. There has to be something that follows it. But whenever I'm talking, just to save a little bit of breath, you're often going to hear me say derivative of secant is secant tangent. But again, I really mean secant of x for each of these trig functions, for example. So we have our 6 trigonometric functions. Has anyone noticed a pattern in how I wrote these and presented them exactly? Let's start with some obvious patterns. So what is one thing you may notice between what I have on the left versus what I have on the right? Yeah, that's probably the first thing I would notice. On the left, all 3 appear to be positive. And on the right, all 3 appear to be negative derivatives. Whenever I tell people to study these 6 trigonometric function derivatives, I usually tell students, if you know the left 3, then you will know the right 3. Because as it turns out, the 3 on the right, you can imagine that they are just the negative co-function version. Sine, cosine, cosine. If you want to think yes, cosine, that becomes sine, and it's negative. Same thing's happening for the second row. tangent, cotangent. Secant squared, negative cosecant squared. Secant, secant, tangent. Cosecant, cosecant, cotangent. Also being negative. So really, the three on the left are your primary ones that we use a lot, because the three on the right are just, I don't want to use the word derivatives because they're related in the same way. And they're actually related because these are some other properties that I won't go into about being co-functions. So again, if anything, if you don't want to try to remember all six, at least bare minimum, try to remember the three on the left. Because you can get the three on the right by taking the co-function and negating the expression. All right, so this is great. We have 6 trigonometric derivatives. And what did we cover for the past 2 days? 3 days, I guess. Before and right before the exam 1. 2 special rules. Product and quotient rule. Well, what better way to introduce our trig functions by also combining trig functions with product rule and or quotient rule, and maybe with some power rule involved in there somewhere as well. So we're building up all of these derivative rules, and we're trying to mix them together and expand our set of functions that we're able to differentiate. All right, so hopefully you have these down. Let's go ahead and do an example. Let's go ahead with a little bit of a proof first. Prove to me that the derivative of tangent of x is equal to secant squared of x. And I claim you can do this without the limit definition. And I'm going to start y'all off by reminding y'all of one special identity in trigonometry. So there's a special identity in trig that involves tangent. If you don't remember this, that's fine. But there's an identity called the quotient identity, not the quotient rule, quotient identity, that says tangent of theta is equal to sine of theta over cosine of theta. This was a rule that happened in trigonometry. So using what I have there, let's go ahead and get the derivative of tangent. So let's go ahead and just call, not f prime, f of x, my bad. Let's call it f of x, let's call it tangent of x, which we know to be sine of x over cosine of x, using that trig identity. Well, if I look at sine of x over cosine of x, that is a quotient. I'm dividing, right? So if I want the derivative of tangent, I need the derivative of this quotient, which means I need the quotient rule. And we're going to do it this way. If I'm using quotient rule, what's my high from here? In other words, what's the top? Yeah, let's go ahead and do it this way. If my high is sine of x, what's my low? Yeah, in this case, my low is cosine of x. I know for quotient rule, I'm going to be taking the derivative of each of these individually, so let's go ahead and write them. What's the derivative of sine again? Yeah, cosine of x. That's what we proved last time. What is the derivative of cosine? Yes. So the way that we could have remembered this is cosine is the co-function of sine. We know the derivative of sine is cosine, so I take the negative co-function version. All right, so I have my high, low, d high, d low. Now I'm going to use my quotient rule. Quotient rule states that the derivative of a quotient is the low, times the d high, minus the high, derivative of the low, all over low squared. And we're going to clean this up. What's cosine of x times cosine of x? Cosine squared of x, right here. Negative times the negative for the other part, we get a positive. And we get sine times sine, which is sine squared of x. All over cosine squared. Does anyone remember what cosine squared plus sine squared of x is equal to? It's equal to a special number. Yeah, correct. It's 1. This is a trig identity. Again, I'm referring a lot to trig identities. Whenever we actually start working on other problems, I'm not going to be expecting you to know these trig identities. I'm using it for the theory buildup. But cosine squared of x plus sine squared of x, that is exactly 1 over cosine squared of x. We could, the thing is that if I wanted to cancel out cosine squared of x, I would split it into 2 fractions. Cosine over cosine plus sine over cosine. It does work in that way, but it relies on a different identity. The last thing I'm going to do here is 1 over cosine of x. That's another special identity. What was that? Yeah, so from trigonometry, we had these reciprocal identities. 1 over cosine was the same thing as secant. Or in this case, we get secant squared of x. And that was exactly the derivative that I showed on the previous slide. So really, if you want to take it even further, all 6 of your trig derivatives stem from what is the derivative of sine. The derivative of sine, you can get the derivative of cosine. If you have the derivative of sine and cosine, you can get the derivative of tangent. If you can get the derivative of tangent, you can get the derivative of cotangent. Same thing, a little bit more complicated for secant and cosecant. So y'all did a little bit sort of a proof here. So this is great and everything, but let's actually get to actual problems where I'll be saying, find me the derivative instead of proving me something or lay out some theory. But before I do that, any questions about what I have written here? I'll give y'all some time to copy any of this down as needed before moving on. The good news about these derivative of trig functions is that it's going to be not as much calculation as we would expect. Remember, for power rule, we had to multiply it down, and we still technically did some calculation work, although it might have been straightforward, like 3 times 4. Here, we didn't really do much on the calculation end. But on the other end, this proof in particular required knowledge of some trigonometric identities. Yes. Something equal to 0. There's not one coming to mind for me. You might be thinking of the trig function at a certain angle. Like if we do like, let me think real quick, like sine of 0, we get 0. Or like sine of 180 degrees, we get 0. You might be thinking of like the unit circle thing where we check all the angles and stuff like that. There might be one that I'm not thinking of for trig identities. If you can find it and show it to me, I can definitely explain it. But I can't think of one off the top of my head that's turning out to be 0. Um, yeah, I'll have to look and see what's happening for that one. All right, so we got this example 1. Let me clear this. Example 2. Let's get some derivatives. Like I mentioned before, most of this unit is going to be, hey, here's a function. Give me the derivative. This is a prime example of something I could give. Let's say I've got y is equal to 3 sine of x plus 8 cosine of x. And once again, I just want the derivative. So if I'm looking at y is equal to whatever, the derivative is dy dx, or if you want, you could also just say y prime. It's just a matter of preference, whatever you personally prefer. I'll take either y prime, or you can say dy dx. These both mean the same thing for us. Remember how we had f and an f prime? That's where the y prime idea is coming from. So looking at this, remember coefficients go along for the ride in differentiation. So I'm just going to go ahead and write down my 3. Because remember, coefficients, they don't really change. They might get multiplied later on, but I can bring them down. What's the derivative of sine? Yeah, so derivative of sine, we get cosine of x. Whenever I'm talking about, I'll say cosine, but again, we mean cosine of x. Plus 8, what's the derivative of cosine? Negative sine of x. And if I want it, technically, I could clean this up. Really, all I can do is move this negative up front. I'll just simplify this one. Usually I won't, but this one, because it's just a single step simplification. Great. We just got the derivative of a trig function. And pretty soon, you'll probably figure out that the most ideal trig functions for us to work with is sine and cosine. Sine and cosine is usually what I have students asking me to give questions on instead of the other 4, because the other 4 tend to be a little bit more work. All right, so any questions about this quick part A? We'll move on to part B in just a moment. All right, let's go ahead and look at part B. K of theta is equal to 17 sine of theta cotangent of theta. Remember, even though I'm using theta here, it just means another variable. It would be the same thing if I just wrote K of x is equal to 17 sine of x cotangent of x. The actual choice of the variable is pretty arbitrary for us. So I want K prime of theta. So what type of rules do you think I'm going to be using for this function to get the derivative? Yeah, I'm thinking product rule because I got 2 trig functions being multiplied together. So I know for product rule, I need to label what's my first and what's my second. So what should I label as my first here? Yeah, we can do sine of theta. And if I want, I can just put a 17 sine of theta, just so that we have the whole thing. And then whatever is remaining should be my second. And once again, just like before the previous problem, so that we have it, I'm going to label these out. We said first was 17 sine of theta, and second was cotangent of theta. So I need the derivative of both of these. So what's my d first, derivative of the first? Yeah, so first off, derivative of the first means I want the derivative of 17 sine of theta. First off, the 17 is going to stay. The derivative keeps my coefficient unless it gets multiplied later. And now I just need a derivative of sine, which we now know to be cosine of theta. Great. Now let's look at our second. Second is cotangent of theta. Looking back at that, those 6 trig derivatives, what's the derivative of cotangent of theta? Yeah, negative cosecant squared of theta. For your notes, if you prefer putting x's instead of thetas, that's perfectly fine. Like I said, the variable is arbitrary. I could have easily put a zeta here instead of a theta, or whatever Greek letter or alphabet letter that you wanted. All right, so I did this because I know I'm using product rule. And I know that product rule is first d second plus second d first. So derivative of this product is the first. D second. D second is negative cosecant squared of theta plus the second derivative of the first, 17 cosine of theta. We have our derivative. Granted, unsimplified, but it's a derivative is a derivative. One thing I will note, if you are, for example, doing homework, we don't have homework yet, and you try to put this function into like a derivative calculator, it may give you an answer that looks slightly different than what I have here. This is primarily because a lot of times those online calculators, they do simplify and use trig identities to try to simplify as much as possible. So it is highly unlikely that an online calculator will give you this exact expression. It'll give you something that's still equivalent, but it'll just look different. What was that? Yeah, this is the unsimplified answer. Online, they'll probably give a simplified form or simplified in a different way. And again, you're starting to see examples on why I don't want y'all to spend all this time cleaning up your algebra and stuff like that, cleaning up stuff like this, because I'm worrying more about the calculus. Do you know how to get the derivative? Questions about this part B? Secant times tangent. 17 secant times tangent. Well, the primary reason is that if I look at this, this is still basically a product. And we know that the derivative of a product is not just me taking the derivative of each one and then multiplying it. We have this special order that we have to follow using the product rule. The other reason is that if we did it in a similar way like that, let me do it this way. One way that I'll explain this is that if you had 17x, right? Technically, this is still a product. It's 17 times x. Well, if I did it in the way, sort of the way that you were mentioning, what's the derivative of 17? So the derivative of a constant? Yeah, the derivative of this one would be 0. Derivative of x would be 1. So if we did it that way, then the derivative of every function we know would just be 0. Similar thing here. If I just did the derivative of sine times the derivative of cotangent, that's actually going to give me something completely different. So this is probably one prime example why we have the product rule. Because if I just took the derivative of each part of the product, then the derivative of everything would be 0. All right, so this was example 2, part B. Let me see if there's a part C here. Let's see. I don't think we have enough time to really finish this example for today. So I think we'll end it here for today and then follow up on this on Monday. So I'm thinking on Monday, I'm going to go ahead, on Monday, I'm going to post our new homework assignment that covers power rule, product rule, quotient rule, and maybe a little bit of this trig function stuff. So that's something to look forward to on Monday. Let me go ahead and pause this.